So I wanted to do another differential equation and of this homogeneous type, and then I just want to talk for a second about like why that method works and why you should expect it to work. So let's look at this one here. This is number 22. Real nasty looking problem, allegedly 13 marks. So you know there's going to be kind of a lot going on there. So we've got this differential equation, we've got this initial condition, we're also told that x is positive. So the first thing is I notice that this is a differential equation and that there are some fractions y over x. And so I make the substitution v equals y over x, because that allows me to rewrite my differential equation in terms of just a single letter instead of multiple letters. But if I make that substitution, then I also need to figure out what dy dx is. So if I multiply by x, I get that. If I take the derivative of the left side, I go f prime g plus f times g prime, and that's going to equal dy over dx. So this is equal to dy dx, and so is y over x plus y squared over x squared. So I can set these two pieces equal to each other using this substitution. So I'm going to say that v plus y squared over x squared is v squared. So that's y over x plus y squared over x squared. And that has to equal v plus x times dv dx. That's great. I can subtract v from both sides. Then I have x times dv dx equals v squared. So I can separate my variables. The way to separate my variables is by dividing both sides by v squared, dividing both sides by x, multiplying both sides by dx. So we end up with 1 over x multiplied by dx equals 1 over v squared dv. Some people like to write dx over x and dv over v squared. It's fine to do that. I've just found sometimes that throws people off when they're trying to follow. Okay, 1 over x. We know the integral of 1 over x is natural log of x. We've done that lots of times. Put a plus c on it. Now please, the most common mistake I have seen lately is people saying that the integral of 1 over v squared is natural log of v squared. It's not the natural log of v squared. Think about what happens if you take the derivative of the natural log of v squared. You do not get 1 over v squared because of the chain rule. Please remember that 1 over v squared is the same as v to the negative 2 power. So you add 1 and divide. Great. I'm going to now rewrite that, multiply by negative 1, so I get negative natural log absolute value of x. I can still call it plus c because I just multiplied it by negative 1. So the old plus c is now just the new plus c made negative. And that's going to equal v to the negative 1. Also, because they told me that x is positive, I don't need the absolute value bars anymore. So I'm going to do just one more step where I get back to in terms of x and y. Remember that v is y over x, so v to the negative 1 is just x over y. Okay, before I solve for y equals, I am going to find the value of c in this format here. They tell me that y is 2 when x is 1, so that means that I can solve for c by going negative natural log of 1 plus c equals 1 over 2. In other words, c is 1/2. When I look at this format right here, I can solve for y using 2 steps. Multiply both sides by y, and then divide both sides by negative ln x plus c. So what that means is, this problem wasn't so bad. My final answer is y equals x over negative natural log of x plus 1/2. And there you go. There are, of course, other little things we could do to that. So like sometimes they'll be like, show your answer is in a certain form. And so maybe they would like multiply top and bottom of the fraction by 2. maybe you'd be asked to show that it's in this form. Or maybe they might ask you to use like a log rule, the fact that multiplication in front of a log is a power. So you could do something like that, and I don't know why you would do that, but they could maybe ask you to do that. So those are all equivalent ways to do it. Okay, so this trick, when I first saw it, I was like, who would think of that? Why would that work? Does it always work? Those sorts of questions. And so what I want to do is just do a homogeneous equation just sort of in the abstract and show you why you should expect this to work with some caveats. So when do you use this substitution? You use this substitution when you have a differential equation where the derivative is equal to some function of the ratio y over x. And if that's the case, then we say, oh, okay, let's let v equal y over x, and we do our, x times v equals y, and we get that v plus x dv dx equals dy dx. And so then we get this general situation, v plus x times dv dx equals f of v. And that doesn't really seem like a better situation, but this situation is now separable. If you subtract x from both sides, which is something that I did in the example, I get f of v minus v. And then if I, just like in the example, multiply both sides by dx and divide both sides by x, I'll scoot over to the other side of the screen here, I end up with this. I have dv over f of v minus v equals dx over x. We know how to handle dx over x. We know that dx over x is going to be natural log absolute value x plus c. So the only real question is whether or not you know the integral of 1 over f of v minus v dv. If you know how to do this integral, then you can solve this homogeneous differential equation. If you can't, then you're just going to be stuck. But that is this, what I'm showing you here in the abstract is why this substitution takes a differential equation that is not separable and changes it into one that is separable. And once it's separable, then it stops being like a differential equations challenge and just switches to being like, are you able to integrate this thing or not? Okay, so if you're thinking of like the units in IB math, it's like it was a chapter 8 problem, a differential equation, and then you do the substitution v equals y over x, and it changes into a chapter 7 question where it's just, are you able to integrate it or not? All right, so that's it. Please let me know if you got any questions. Thank you.